I want to start this section off with a very important trigonometric identity. So this is a diagram we saw in 6.1 where we have a unit circle. It's a circle centered at the origin with radius 1. And you can see the angle theta there measured in standard position. And if you recall, our new interpretation of cosine and sine is simply the x-coordinate and the y-coordinate of the point P as you move around the circle. So the horizontal leg of the right triangle is cosine theta, the vertical leg is sine theta. Now, it's a right triangle, and for many years now you've known something else about right triangles, which is that they satisfy Pythagoras. So let's apply Pythagoras to this right triangle. If we square one leg, the horizontal leg, which is cosine, when you square cosine, you put the exponent right beside the cosine, and this is to avoid any confusion as to whether you are squaring the cosine of theta or whether you're trying to take the cosine of theta squared. So if you just put the squared beside the cosine, there's no confusion. So cosine squared theta plus sine squared theta, that's the sum of the squares of the two legs, is equal to the square of the hypotenuse. Well, the hypotenuse is just 1. Now, this, as I said, is a very important trig ratio, and you're going to spend a lot of time looking at this and other trig ratios in Pre-Calculus 12. You're also going to need this to understand what we're going to do at the end of the chapter, which is the cosine law. So this doesn't necessarily have that much to do with what we're going to do for the rest of today, but keep that in mind. Now, let's take a look at angles in standard position in all quadrants. There's one definition you have to learn, which is that of a reference angle. So a reference angle is the acute angle between the terminal arm and the x-axis. So I'll give you a couple of diagrams to understand this. So it's always going to be an acute angle. It's always going to be between 0 and 90 degrees. And we can, again, think of a terminal arm. If we have a terminal arm here in quadrant 1, then the terminal arm and the reference angle and the angle measured in standard position are the same because the angle measured in standard position is already acute. But if we are over here in quadrant 2, theta as measured in standard position is bigger than 90 degrees. And so I'm going to refer to the reference angle with alpha. Alpha is this angle here, and in this case alpha is simply equal to 180 minus theta. Because if you go halfway around, you're at 180 degrees, or if you think of that as a straight angle, theta plus alpha adds up to 180 degrees. So in quadrant 3, which is in the lower left-hand corner, again, theta now is bigger than 180 degrees. Alpha is just this little part here. And so you can think of alpha as theta minus 180 in this case. This is quadrant 3. And what about if we're down in quadrant 4? So if we're in quadrant 4, theta is somewhere between 270 and 360 degrees. Alpha is this angle right in here. And so obviously alpha is just 360 minus theta. 360 would be all the way around, full circle. You're sort of not quite going full circle, you're backing up alpha. So alpha is just 360 minus theta. Okay, so what do we need the reference angle for? In some senses, this is a bit of an archaic concept. In the days before scientific calculators, you would have to look up sine, cosine, tangent in a table, and they wouldn't provide a table that had every possible angle. They would simply list all the angles between 0 and 90, or sometimes if they really wanted to save paper, between 0 and 45. And so if you wanted to find an angle, sine or cosine of an angle bigger than 90, you would have to first determine this reference angle, and then look up in the table the sine or cosine of the reference angle, and then use some relationships that we will explore. Now, I like to do it a little bit differently, and if you understand the concept of sine and cosine being simply the coordinates of a point as you work your way around a circle, then you should develop a fairly intuitive understanding of whether the sine should be positive or negative, whether the cosine should be positive or negative. And we're going to explore that in a number of different problems right now. So, without talking too much more about the reference angle, I'll bring it up at times in the problems, but I won't refer to it specifically. Let's take a look at some trig equations. And you've seen these sorts of equations before, but there's going to be a bit of a wrinkle to them now. Let's imagine you have sine theta equal to half. As I said, you've seen equations like this before. To figure out theta, you would just use the arcsine, and you would reach for your calculator, or perhaps you know the value. Arcsine of a half gives you theta. But when you see the equation now, there's going to be another statement, which is 0 is less than or equal to theta less or equal to 360 degrees. In other words, to solve this equation, we're looking for all values of theta that have a sine of a half. And there's going to be 2 for most of these equations. So, how do we do this? What I want you to do immediately upon seeing these equations is ask yourself, is sine associated with y or with x? Sine is associated with y, so what we're really looking for is where, on a unit circle, is the y-coordinate equal to a half. So of course, the next thing you have to do is draw your unit circle. And it doesn't have to be perfect, it just has to be a rough sketch. And now you have to think about where on the unit circle is the y-coordinate equal to a half. Remember that the 4 cardinal points here that we can label are easy, right? This is 1, 0. This is 0, 1. So in other words, at the top of the circle, the y-coordinate is 1. And along the x-axis, the y-coordinate is 0. So where is the y-coordinate a half? Well, you can draw the line y equals a half, which is a horizontal line, and that helps you. And just draw it so that it crosses the y-axis about halfway in between the origin and that point at the top of the circle. And then label those points, or at least indicate those points on the circle that intersect with the line, because those are the 2 points on the circle that have the y-coordinate of a half. Now, if you draw in the terminal arms, you can start thinking of the angles. So where is... Well, at this point, you probably should reach for your calculator if you don't know what theta is based on the value, and do exactly what you did last year, which is write, well, okay, theta is equal to arc sine of a half. And what you'll find is you get exactly 30 degrees, which means that this angle here is 30 degrees. We can also refer to this point on the circle as 30 degrees. Now, you can see there's another point. The calculator is never going to give you that point directly. You have to determine it. And one way is to memorize a lot of relationships. Another way is just to do this sort of diagram and understand that the sine value is really just the y-coordinate. Now, there's an obvious symmetry to this diagram. The left-hand side is a mirror image of the right-hand side. The y-axis is a line of symmetry. And so that 30-degree angle over on the right-hand side is the same as this 30-degree angle over on the left-hand side. Now, that 30-degree angle that I just labeled, we could call a reference angle. All right, it's a reference angle for an angle in standard position that is clearly bigger than 90 degrees. So how do we figure out what that actual angle in standard position is? Well, you can think of going full circle, or at least half circle, which would be 180 degrees, and then backing up 30 degrees, or just not quite going that last 30. And so you can see that in standard position, this angle is 180 minus 30, which gives you 150 degrees. So the two angles that are solutions to this equation are 30 degrees and 150 degrees. Now the nice thing about these equations is that it's very easy to check. You just simply have to pull out your calculator and take the sine of 30 and the sine of 150 and verify that they're both approximately a half, and in this case they're actually going to be exactly a half, but in many cases you're not going to get exactly the value that you're looking for. But the two values should be identical, and sine 30 and sine 150 both give you exactly a half. All right, let's try this again for a cosine equation. Let's say we have cosine of theta equals half. I'll use a half just for consistency, but we can do some others a little later. Again, theta, we're looking for all values of theta between 0 and 360. So what's a cosine associated with? Sine is associated with y. Cosine is associated with x. So really, this equation is asking where on a unit circle is the x-coordinate a half. So we need to draw our unit circle. Again, doesn't have to be perfect, just a sketch. X equal to a half is a vertical line. And remember, this point over here has an x-coordinate of 1. Anything on the y-axis has an x-coordinate of 0. So we want to be halfway in between the y-axis and that point on the far right of the circle. And that's where we're going to draw our vertical line, x equal to a half. I'll label the 2 points. And you can see there's one point up here in quadrant 1 and one point down here in quadrant 4, which is going to be an angle somewhere between 270 and 360. So at this point, if you don't know what angle theta is, you can reach for your calculator and do theta equals arc cos of half, and you'll get 60 degrees. So that means that this angle here measured in standard position is 60 degrees. And once again, your calculator is never going to give you the value for that angle down in quadrant 4, at least not directly. You have to rely on this diagram, or you have to remember some relationships. And I think it's far easier to just simply remember that cosine is associated with x, sine is associated with y. Otherwise, it's just too easy to get confused with trying to memorize all the other relationships. So there's symmetry in this diagram, but it's not left-right symmetry. The top is the mirror image of the bottom. The line of symmetry is the mirror line is the horizontal axis, the x-axis. And so this 60 on the top is reflected down here. So the point on the circle up in quadrant 1 we can refer to as 60 degrees. Down in quadrant 4, if we liked, we could actually refer to that point as negative 60 degrees. You're going 60 degrees in a clockwise direction. And in fact, if you pull out your calculator right now and do the cosine of negative 60 degrees, you'll see it tells you it's exactly a half. So it's fine. The only problem is we're not looking for values of theta between, or that are negative. We're looking for values that are between 0 and 360. So we have to think of this point as measured in standard position. So we have to go all the way around the circle, and it's going to be something bigger than 270. Now, if we did the full circle, it would be 360, but we're not quite doing a full circle. You can think of backing up 60, or just not quite going that last 60. And so you get 360 minus 60, which is 300. And so the values of theta that satisfy this equation are 60 degrees and 300 degrees. And again, for the angle of 300 degrees, the reference angle there is 60, because that's the angle between the terminal arm and the x-axis. All right, let's try one involving tangent. Now, we first have to understand something about tangent. If you recall, just from the right triangle trigonometry that you learned, that the sine is equal to the opposite over the hypotenuse, and the cosine is equal to the adjacent over the hypotenuse. What's the sine divided by the cosine? Well, the h's there cancel out, and you get opposite over adjacent. But from our acronym, SOHCAHTOA, we know that opposite over adjacent is tan. So, in fact, the tangent is simply the ratio of the sine to the cosine. And since sine we associate with y, and cosine we associate with x, we can think of tan as associated with the ratio y over x. So when you get an equation involving tan, just for consistency, well, actually, I'm not going to use a half. Let's use tan theta equal to 1. Immediately, you can write y over x equal to 1. Now, if you multiply both sides of that by x, you get a very straightforward equation of a line, y equals x, which is not a horizontal or vertical line. It's an inclined line. It has a slope of 1, and it passes through the origin. So, we can draw a unit circle. And what we're really trying to find is where on the unit circle is the ratio of y to x equal to 1. It's a lot easier to think of drawing that line, y equal to 1x. And that will tell us exactly the 2 points. You can see there's one point up there in quadrant 1 and one point down in quadrant 3. If you think of tan as the ratio of sine and cosine, then there's a relationship between quadrants 1 and 3 and between quadrants 2 and 4. Sine, as the y-coordinate, is positive in quadrants 1 and 2 and negative in quadrants 3 and 4. Cosine, as the x-coordinate, is positive in quadrants 1 and 4 and negative in quadrants 2 and 3. So the ratio, when you have a positive over a positive, the tan is going to be positive in quadrants 1 and also down in quadrant 3 where the sine and cosine are both negative. Alright, so in tan you get relationships that sort of go diagonally. Now, if you don't know the value of arctan 1, reach for your calculator now and figure out what theta is. Arctan 1 gives you a value of 45 degrees. So this angle here, as measured in standard position, is 45 degrees, and that point on the circle we can refer to as 45. This diagram has symmetry, but it's not a reflection, it's a rotation. And this, if you rotate it 180 degrees, you get 45 degrees there. And so again, that 45 degrees that I just labeled is the reference angle for the terminal arm down in quadrant 3. So how do we figure out how to refer to this point down here in standard position? Well, if you go halfway around the circle, you're going 180, and then you're going an additional 45. So you've got 180 plus 45, and that gives you 225 degrees. So the angles here that solve this equation are theta equal to 45 degrees, or 225 degrees. And again, very easy to check. You can plug in tan 45, tan 225, and you should get a positive 1 in both cases.